standing for System International. What's the only country in the world that doesn't regularly use the metric system? The United States. Okay, a president decided that they wanted to adopt our own measurement system, and so we use our own. Even though for science we have to convert everything, because if we didn't, then no one else would know what we were talking about. So the SI system or the metric system is used universally, and really it's used for science. The reason we use it is that so if we share research with other countries, they have to know what units we're talking about. Okay, and so we convert everything into the metric system. The U.S. system does not go in powers of 10, right? We have 1 foot, that's 12 inches. We have 16 ounces in a pound. Whatever. Crazy stuff. All right. Just a reminder, when we're taking notes in physics, main concepts, right? You don't have to write down every single word that I write up here. Main concepts and every equation. Okay? Those are what we're looking for. So here are what we consider the base units, or the most commonly used units for each type of measurement we would want to take. I would write down the top 4. We don't need these guys. You need to know that if you want to measure length, it's usually going to be in meters. If you want to measure mass, it's usually going to be kilograms. So when I say base units, those are really the most common units for that measurement. I don't want you to confuse base units with the middle or the base of the metric system prefixes. I'll talk about that in a second. Okay. Meter, kilogram, second, and Kelvin. Anybody know anything about Kelvin? Yeah, Joe, what do you think? Do you remember what the conversion is between Kelvin or Celsius? Plus 273. Close. 273. Okay? So 0 degrees Celsius is 273 Kelvin. Okay? Kelvin is just like... it has the same ratio as Celsius. So if Celsius would increase by 1 degree, Kelvin would also increase by 1. Do you call it degrees Kelvin? No. For some reason, no. It's just Kelvin. Degrees Fahrenheit, degrees Celsius, and Kelvin. I don't make the rules. Something that you should also notice is that seconds is just abbreviated with an S, not SEC. It's kind of habit for us to want to write SEC for seconds, but it's just an S. Okay. Why do you think the base units for mass are kilogram rather than gram? Every other unit is just it by itself with no prefix. Yeah, what do you think? Yes, I think what you're trying to say is. Maybe I'll... Make it more specific? Yes, kind of. Okay. Grams is a really, really small unit. So for all intents and purposes, we will be measuring things that weigh over 1,000 grams, right? Most things that are measured are over 1,000 grams. So rather than deal with a measurement that says it's 4,900 grams, it's much easier to say it's 4.9 kilograms. It puts our numbers into a more approachable value, I guess. I don't know. Just gives us a little easier numbers to deal with. That's it. It's just that kilograms is easier than grams. So, all right, now I want to look at the metric system and the prefixes. And I'm going to show you this chart because this is what you see almost everywhere, and then I'm going to rewrite the chart in a way that makes more sense to me, and I think will make more sense to you. Okay? So just don't copy this down just yet. This is how this chart reads. It says, that 1 megameter is 1,000,000 meters. Are we on the same page with that? It also says 1 centimeter is 100th of a meter. Don't love that. Okay, I don't like talking about fractions or decimals of that unit. The way that my brain processes that is that I need to say that a meter is 100 centimeters, rather than say a centimeter is 100th of a meter. Does that make sense? My brain processes it that way differently. So I'm going to rewrite the table as if, like the way that I would write it down if I were you. Does that make sense? Okay, and I'll write down only the ones we need to know. We need to know the ones in red, and then nano. So I'm going to rewrite the table in a way that makes sense to me, and maybe it will make more sense to you when it's written in that way also. Okay, so the way I would write it looks the same for units bigger than meter. I would say mega, right, is an M, capital M, and I would say 1 mega meter is equal to 1 times 10 to the 6th, or a million regular meters. I want you to understand that these prefixes apply to every type of unit. So if I said 1 megagram, how many regular grams would that be? 1 times 10 to the 6th, or a million, right? The prefixes apply no matter what. I am just using meters as an example to write this chart. That's it. Oopsies. Are we on the same page with that? Okay, so I'm going to move to kilo. Kilo means 1,000. People get this confused a lot, but kilometer is bigger than a meter. So don't say there's 1,000 kilo in 1 meter. It's the other way around. Kilo means 1,000 of the things. All right, so then we're going to write in just kind of a little dash, because this is no prefix. 1 meter equals 1 meter, right? That's like our middleman. That's our base. It would be the same if we were at grams here, or liters, or whatever it would happen to be. So now I'm going to go down a little bit. I'm going to leave off deci because we don't use deci that often. I'm going to go to centi. Okay, and it's a lowercase c. And so the way that it writes now, if I'm keeping meters on the right-hand side, I would say there's 100 centimeters in 1 meter. So you see how there's a flip from the larger unit being on the left to the larger unit being on the right. Okay? So now I would go to milli, and it's a little m. So I'd say 1,000 millimeters is in 1 meter. And then I'm going to go micro. The prefix for micro is it's a Greek letter, I think lambda, and it's just a U with like a little tail on the front. Okay, 1 times 10 to the 6th, or a million micrometers, are in 1 meter. And then lastly is nano. It's just a lowercase n. 1 times 10 to the 9th nanometers is in 1 meter. So this chart makes more sense in my brain because I like to say how many smaller units are in the big unit. Right? That's the way that I will teach my conversions, and that's the way that my brain works. Rather than trying to deal with fractions, decimals, I just don't like that. I'd rather have whole numbers when I can. Agreed? Okay. So those are our metric prefixes. I would highlight that little corner of this page that it's on, put a sticky note in if you want to. I can give you a sticky note to mark this page in your notes. Now, we're going to start some conversions. One of them, the first, is going to be U.S. system. So these are units that we are familiar with. Okay? Second one's going to be metric, and we're going to compare the two. So if I wanted to go 193 inches to miles, did you guys learn a system on how to do unit conversions that looks something like this? Yeah. 193 inches. Oh, yeah. Right? Okay, good. That's how I teach my unit conversions also. Okay, so the way you need to think about this is that I'll take it back a second. If I wanted to go 193 inches to mile, I would go inches to what? Feet to what? Miles. And so to go inches to feet, don't write this down, just watch this for right now. If I wanted to go inches to feet, what do you know the obvious thing I need to do is to do what? Divide by 12, right? And I get some number there. Okay, which I need a calculator out so I can show that number. But if I wanted to go inches to feet, I would take 193 divided by 12. And I get what? 16.083. And if I wanted to go feet to miles, what would be the obvious thing I do? divide by the number of feet that are in a mile, right? And I get 16.083 divided by 5,280. If you don't know how many feet are in a mile, write that down. 0.00304, whatever. We can round that as far as we want. That's the way I do that. And that works for conversions that we feel comfortable with. But I'm going to show you now what we did is basically fraction reduction twice. Right? Does that make sense? All we did is basically multiply fractions together. And then we reduce them. So I show you this system that we can do it all in one place without having to plug a bunch of things into our calculator multiple times. Okay? So we know we want to go from inches to feet. If I have inches in the numerator, where does it need to go in order to cancel? In the denominator. So we put that in the denominator. I know I want to go 2 feet. I would go ahead and write this out. Yeah, this is the way that I will teach conversions, and you'll see me do it consistently this way. Okay? So how many, this is how I do mine also right here. I give the bigger unit the 1. So between feet and inches, which one's bigger? Feet, right? It would make more sense for me to say how many inches are in 1 foot rather than say how many feet are in 1 inch. Right? That would be silly to do it that way. Okay? So I go 12 inches in 1 foot. Inches have canceled. So if I stopped my math right now, 193 divided by 12, I would be in feet. That's not what I want. I want to go feet to miles. Make sure you put MI. Just an M is meters, right? That's not what we want. So again, should I say how many miles are in 1 foot? No, that would be silly to do it that way. I'd say 1 mile equals 5,280 feet. Okay, so especially you international students, if you haven't heard that conversion, 1 mile equals 5,280 feet. Maybe put that under your chart from the metric system. All right, so now I'm going to check my units. I canceled feet, I canceled inches, I'm left in miles, that's what I want. The top right unit should always be what you want your answer in. Okay, if I want to end in miles, it should always end up right there in my t-chart. All right, now to do the math, I multiply across the whole top, divide by the whole bottom. So 193 times 1 times 1, don't really need to do that. Divide by 12, divided by 5,280. And we should get exactly the same answer. Okay, I'm just showing you this is the process that I will go through. So what happened in your calculator?
12 times.
You did 12 times 5,280 without parentheses. So your calculator took 193 divided by 12, and then it took that whole answer times 5,280. You need to put parentheses around your denominator.
No, I just did 12 times 5,280.
Oh, my bad. You haven't divided 193 by that yet. That's my fault. Okay, I misunderstood that. Okay, the way I will plug this into my calculator, I'll go 193 divided by 12, and then I just hit divide by 5280, enter. That's it.
So you do
multiply across the whole top, divide by the whole bottom. And what since these are ones, right, I could plug in 193 times 1. I don't need to do that. So I go 193, and I go divide by 12, and then without hitting enter or anything else in my calculator, I hit divide by that. I don't ever retype things back into my calculator. That's too much work for me. Okay? So I just like to do it in as few steps as possible. If you did not get that answer in your calculator, let me know so I can please help you figure that out. Okay? Let's try a metric system one now. Millimeters to meters. Some of you might not even need to write this out, but I'm going to do it for everybody. So 1382013 millimeters to meters. To go from millimeters to meters, do I need to stop at centimeters along the way?
No.
No. You go ahead.
Well, you don't have to stop this, and we already know how many.
Perfect. We know exactly how many millimeters are in a meter. If we have a direct conversion, use that. Okay? So I know that 1 meter is 1,000 millimeters. So all I do is divide by 1,000. That's it. 1382.013 meters, right? Which one was easier? The second one, right? The metric system one's easier. Everything is thousands or hundreds. All you have to do is move the decimal. We'll get conversions that are several steps, right? Not just two, or not just one, I mean. But in general, the metric system is much simpler. Much fewer things to memorize in terms of conversion factors. This table you should have in your notes. Almost all of them give the bigger unit the 1. The only exception I have, and I don't really know why, it's just because this is how I memorized it, is feet and meters and pounds and kilograms. Okay, otherwise the larger unit always gets the 1. You're welcome to change that conversion if you want, but that's just what I have memorized and that's what I'll use most often. All right, he ran 2.433 kilometers. How many centimeters did he run and how many miles did he run? So we're going to do centimeters first. 2.433. You don't have to write out the whole word problem, right? We're just doing practice here. Do I know, just looking at my chart, how many centimeters are in a kilometer? Without doing any math. I'm asking you to do no mental math here. On my chart, does it say this many centimeters equals this many kilometers? No. What's the middleman? Meters, right? So in my chart, I'm going to say I need to go kilometers to meters, then I need to go meters to centimeters, and then I go fill in my numbers, right? I know some of you can move the decimal place. That is perfectly fine, okay? But here, which one gets the 1, kilometers or meters? There's 1 meter in how many kilometers? So there's 1,000 kilometers in 1 meter?
Yeah. What?
Nope, that one's backwards, and it happens all the time. All the time. That's okay. It happens so often. Kilometers is bigger. There's 1,000 meters in a kilometer. Then between meters and centimeters, which one is bigger? Meters, right? And then we go 100. So we check our units to make sure we didn't put anything upside down. Kilometers, kilometers, meters, meters. We're left in centimeters. Run the math, which should end up with 243300, I think. 243,300 centimeters, possibly. Everyone got how I got the math there? Just multiply, and then you divide by 1, which is nothing, right? Or not nothing. You just don't have to do anything. Okay? All right, good. That's where we're going to stop today. All right, so kilometers and meters, which one gets the 1? Kilometers, good. And I say there's 1,000 meters in a kilometer. Between meters and feet, I know that meters is the bigger unit, but in the chart, I have it backwards because that's how I was taught and that's how I memorized it. You can do it either way, but you do need to know that 1 meter is not exactly 3 feet. It's close, but it's not exact. So I say 1 feet is 0.305 meters. That's the only one that I do backwards consistently where the bigger unit doesn't get the 1. So sorry about that, but too bad. 5,280 feet are in 1 mile. Man, my technology is lagging today. Okay, so now to do this math, I multiply across the whole top, divide by the whole bottom. Have we plugged that in yet? What did you say? Oh, you already got it? Okay. It's okay. Kilometers, meters, feet, left in miles, right? The unit that I want always needs to be top right of my T-chart. Okay, so 2.433 times 1,000. Then in my calculator, I would go divide by 0.305, divide by 5280, so I don't have to re-enter anything. I got about 1.49 miles. Cross-country runners, does that seem about right? Right, a 5K is roughly 3 miles, a little over 3 miles. Right, so we're running a little under half of a 5K. So.
What did you say the number you got was?
I got 1.49 miles. Sorry, is that? Can you see the board? I just want to make sure it's not cutting. Okay. If you did not get that in your calculator, I want to know so that I can help you plug it in. You either need to put parentheses around your denominator or you need to do divide by, divide by. Okay, yeah?
I got...
Try this one on your own. How many seconds are in a leap year? It didn't even give you a number to start with. What do we know about a leap year?
63 days.
Nope.
65.
Nope.
64.
Nope. 66. 366. Regular year's 365. Leap year's got one extra, so 366 days. So we need to go 366 days to seconds. I want you to start doing that in your own T-chart, and we'll come around and help.
Tell me what you get.
Oh, it's lagging a little bit, but let's see. 31,622,400 seconds. Raise your hand if that's what you got. Good. All right. Very good. Questions about that? Meters to miles first. So we just talked about we could go meters to feet to miles, or we could go meters directly to miles. If I know that there's roughly 1,600 meters in 1 mile. If you want to go meters to feet to miles, that's perfectly fine. But we know there's roughly 1,600 meters in a mile. Okay? Which means I have canceled meters. If I stopped right now, what would my units be? Miles per second. And is that what we want? Mm-mm. So we keep going. And now if I want to get rid of seconds, where does it need to go? In the top, right, on the top. So I can go seconds to minutes. And if I stopped right there, my units would be miles per minute, which is not what I want. So now I want to go minutes per hour. So now I check my units, and I'm left with miles over hours, miles per hour. Okay, so now run the math. .93 miles per hour. Oh, man, it is lagging bad. 2.93 is what I got. I didn't just get 2. 2.93. So he's not moving very fast. Questions with unit conversions? All non-zero digits are significant. So in our last example, when we said 14.3 centimeters, the only questions we ever have with significant figures are about zeros, regarding zeros. If we put a digit in there, we assume that we came up with that digit, right? We wouldn't add a 7 to the end of a measurement for no reason, right? Does that make sense? Sometimes people throw on zeros just because they think they need more significant figures. So the only questions that we have with significant figures are about zeros. Zeros to the right of digits after the decimal point are significant. So I'm talking about 0.2 here. If I said it was 24.40 centimeters, how many significant figures do I have? 4, right? All 4. This 0 means I think it's exactly 40. It's still an estimate. The last one's still an estimate, but it's saying I think it's exactly 40. Zeros to the left of digits are non-significant. They are placeholders. So that means those two are non-significant. That's because if this was in like centimeters, I should just change the unit to millimeters. right? I should just change my unit. That would give me a more valid digit. These are just placeholders. So how many significant figures does this value have? 1, 2, 3, right? 3 sig figs. Okay, does that part make sense? Zeros to the left of digits are non-significant. Next one, all digits used in scientific notation are significant. And when I say all digits used, I mean all visible digits. So when I say 1.443 times 10 to the negative 12th, how many sig figs? Just 4, right? If I would expand that out, 0.1, okay, expand, blah, 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 1, 4, 4, then all those zeros would be placeholders. All we're concerned with are the visible digits. Those are all significant. Okay, visible digits in scientific notation are all significant, so 4 there. Is this a valid scientific notation? Is that a valid form of scientific notation? Why not? Yeah, this number in scientific notation must be between 1 and 10. And so that's invalid. Okay, no good. So all digits in correct significant scientific notation are significant. Okay, there are some measurements and some values that we consider ambiguous. And to be ambiguous means we just don't know how many digits in this measurement are significant. Ambiguous values are ones that have what I call trailing zeros. Trailing zeros are these guys, right? We have no idea how exact that measurement is supposed to be. Is it 118.5 and they round it up? Is it 120,000.00000 and it's super exact? Like, we just don't know. So this number, if I asked how many significant figures there are, you wouldn't write 2 because there's 2 digits. You would say it's ambiguous, which means I just don't know. Okay? So this one, for this particular number, there could be 2 sig figs, there could be 6, there could be 8, if there's 2 decimal places, whatever. We just don't know, so we call it ambiguous. Okay, this bullet right here is really important. To fix an ambiguous value, you use scientific notation or you add a decimal place. To fix ambiguous values, you use scientific notation or you add a decimal place. To get the correct number of sig figs. So let's say that I wanted to express this value, 120,000, with only 3 significant figures. Is it possible for me to do that? If I wanted to express 120,000 with only 3 sig figs, don't tell me how yet, but tell me if you think I could do that. Like a yes or a no. Is it possible for me to express this value with 3 sig figs? Yes, it is. How do I do it? 1 like this? 0.00 like that? Okay, all right, good. I'm hearing a couple different things. 12.0 times 10 to the 5th, 4th. What do we think? This guy right here has to be between 1 and 10. Right, 1.2 times 10 to the 5th. Yeah. Yes, you may. Here is this. For our class, it would be due Monday. You're right. That's not 3 significant figures. That's only 2. So what do I need to have? 1.20 times 10 to the 5th. This is my correct answer. Thank you for catching that. 1.20 times 10 to the 5th is my correct significant figures and correct scientific notation. Do any of you struggle with, did any of you want to say negative 5th there? Or we feel pretty comfortable with scientific notation? This value, this exponent is positive anytime our original number is greater than 10. Okay? Anytime our original value is greater than 10, your exponent needs to be positive. All right. Oh my goodness, my computer is having just so many issues. Whew. Okay. All right, now we're going to add significant figures into our math operations. When you add and subtract and you're thinking about significant figures, you do the math just like usual. And then you round your answer to what we would consider the least precise value involved. And I'm going to add a little extra here. Least precise value involved. You're going to look at decimal places. It's going to say places here in like 2 seconds, okay? You need to look at decimal places. When you're adding and subtracting, you're going to round your numbers to the least precise value involved. Here's the reason for that. If you take a group of measurements and you try to make your average or your final measurement more precise than one of your originals, no good. Your average or your answer cannot be more precise than one of your original measurements. That's the reason for that. Okay? So if I was going to do this problem, which I already did the math for you, 12.520 plus 14.0 gives us this raw value. That's the raw answer. If I have to round my answer to the least precise value involved, which one is least precise, 14.0 or 12.520? 14.0, which means my answer can have how many decimal places? My answer can have how many decimal places? 1. It can only have 1, which means my correct answer should be 26.5, right? Does this 2 round the 5 up or down?
Down.
Right? This 2 rounds it to a 5. If it was 26.58, then that would become 26.6. Okay? What questions do we have about adding and subtracting? Add and subtract, you look at decimal places. Multiplying or dividing are when we are considering our significant figures, not just our decimal places. So when we multiply and divide, we do the math, then we round to our fewest number of Sig Figs. Fewest number of Sig Figs. Okay, so adding and subtracting is decimal places. Multiplying and dividing is significant figures. So I'll make a little extra note on here. Least precise measurement or number of Sig Figs. Okay. So I'm going to say this over and over and over again because I think some people will still stumble on it. Adding and subtracting, you look at what? Decimal places. Multiplying and dividing, you look at Sig Figs. Good, least Sig Figs. So, here we go. Let's try one here. Oops. Okay, if I take 2.40 times 12, I get the raw answer of 28.8. How many Sig Figs can my answer have?
2.
It could only have 2 because 12 only has 2. 12 only has 2 significant figures. And so how do I correct that answer? I round it up to 29. Right? My final answer should be 29. Or 2.9 times 10 to the first. You could put it in scientific notation, but I don't put things into scientific notation unless I have to. Okay? Unless I absolutely have to. And for problems like these, you might have to. All right. Try these 2 on your own. Okay, can somebody give me just the raw answer that they got with no rounding, no fixing, no nothing for 139 times 2.3? 319.7. $319.7. So how many significant figures is my answer allowed to have? Only 2. So can I leave it like this? Okay, so tell me what the fix is. Yeah, Emily. Okay, so if I round to 320, perfect. I have to put this in scientific notation because 320, it doesn't have 3 sig figs. It is ambiguous, right? It's got a trailing 0. Do you know what I mean when I say trailing 0?
Yeah.
0 on the end, no decimal.
0 on the left side.
0 on the...
Left side.
Oh, I see what you're saying. As long as there's no decimal. If there was a decimal here, that would count. Okay? So 320 won't work, so my answer needs to be 3.2 times 10 to the second. Right? 3.2 times. How many of you got all the way, got to the scientific notation part? Good. How many of you left it at 320? That's okay. That's fine. I did this one on purpose because that's always something that happens. All right, next one. Give me the raw answer. Stephen, what did you have for the raw answer on number 2?
26.281.
26.281. And what do we need to be looking for here in terms of, this is back to everybody, what do we need to be looking for here in terms of our answers, right? Decimal places. So what should my answer really be? 26.3. I only get to have one decimal place, and that makes that round up. 26.3, and I'm missing one thing. Good, centimeters. Here should have been centimeters squared. Okay. Questions about math with Sig Figs. Is it coming back to us a little bit? Okay. Here's. Put it in scientific notation just like you usually would, but you just got to cut it at 3 significant figures. That's all we're doing here. Put it in scientific just like usual, but then just stop it after 3 sig figs. So it should be 1.24 times 10 to the 5th, right? 1, 2, 3, 4, 5.
You couldn't have 12.4 times 74?
No, this number right here in front of the multiplication sign always has to be greater than 1, less than 10. Yep. Good question. Very common